but I never asked what you did. Actually, not. If you did study insert she doesn't.
Doodles and case, but we'll be fine. Well,
Did you take a midterm?
oh, then, lab exam one is into.
Oh.
I guess this is our. This is
If
our.
you have your own certain grade, like, number one, every GPA that like 1200.
Okay, good morning, everyone. Thank you for being here. So today would be the last, most probably the last day of the discussion PENP, this so-called difficult part of this course. Okay, so what we have learned so far, let's briefly revisit. So we start from NP complete. We provided an informal definition. What was the informal definition of NP complete?
It don't work.
Not at all.
No, just not in.
There is no efficient solution exist. Efficient means no polynomial time solution exists to solve, produce the exact solution for every instance of that problem. That was the first informal definition that we come up with. Next, last day we told another informal definition. But before that, we also studied two kinds of problems: decision problems and optimization problems. Decision problem is you will make decision yes or no, whether that's yes or no. And optimization is you will find out either minimum, maximum distance, or some minimum, maximum, highest, lowest, those things. You are optimizing something. Then we studied verifiability. What was verifiability?
Whether or not the optimization or decision problem can be solved in polynomial time.
You are on the right track. The verification, whether you can verify the solution, the proposed solution, whether that's correct or not, you can verify that in polynomial time. Verifiability, the proposed solution, verification of the proposed solution. So it's not the coming up with the exact solution. It is the verification of that proposed solution. So it's much easier. Coming up with the solution is much harder compared to verify is proposed solution. So verifiability in polynomial time, and we have observed that decision problem, most of the decision problems can be verifiable in polynomial time, but optimization problem cannot be verifiable in polynomial time. Because if that is so, that means you know what is the optimum value. So it's not possible. So verifiability in polynomial time is mostly for decision problems. So from this verifiability, we leads to the concept of complexity classes. Complexity classes, one complexity classes you all know, that is class P, which is mostly easy class. Means whatever we have started before midterm, almost all comes under class P. And means those problems which can be solvable in polynomial time. And since they are solvable in polynomial time, that means they are also verifiable in polynomial time. So class P is solvable in polynomial time as well as verifiable in polynomial time. Next, we studied NP. What is NP? What is NP class?
Problems that can be verified in polynomial.
You're right. Yeah. That we can't say. Till now there is no solution, but maybe next near future there might be some solution. So we can't say any comment on, we can't make any comment on that, but we know that they are verifiable in polynomial time. That's guaranteed. So NP are those problems which can be verifiable in polynomial time, but we can't say anything about their solution, efficient solution. So far there is no efficient solution, but in future there might be or there might not be. Then we talked about NPC, NP complete. We provided another informal definition of NP complete. What was that? Hardest problem in NP. So this is P. If we think of level of difficulty, the bottom one is P, which is the most easy part. Then NP, which we do not have, so far we do not have any solution, efficient solution, but we can verify those proposed solution in polynomial time. And NP complete comes here. Means NP complete is the hardest part of NP. That's one informal definition. We have provided another one. The second point. Yes, I'm recording. Actually, in my previous data structure class, I again forgot to record the session. So they will struggle. No, ignore that. Yeah, thank you for reminding me. Okay, so what the second point we mentioned regarding reducibility.
X is incomplete if all problems in NP are reducible to X.
Right. X is unknown problem. Let's assume X is unknown problem. We don't know about X. What is X? Whether it's a difficult problem or easy problem. Now we know these are the set of NP complete problem. Means set of tall people. We know that set of tall people. Now we don't know whether X is tall or not. We will compare X with some person Y, who is already known to be tall. Y is known to be tall. Y is 6 feet, just assume. We don't know whether X is tall or not. So we'll compare X with Y. And if X is at least as X height is at least as Y, then we can say X is tall people, right? I'm not making any comments with tall or other things. Okay, so X and Y. So we can think of this way. So NP complete, those problems are there, like decision problems, like subset sum. Those problems are known to be NP complete. Now X is new problem that you come up with. Just compare that hardness of X is at least as hard as Y. Then we can say that it's also difficult problem, right? That means we are reducing. Here comes the concept of reducibility. And we need to do this reducibility reduction in polynomial time. So we'll revisit that now. So lastly, we take one example. This was your problem A. And this was your problem B. Now, last year we shown that we can utilize the solution of this problem to solve this problem, right? We can utilize the solution of this problem to solve this problem. How? How we can do that? Make C equals to 0, T equals to A, and E equals to B. Right? Then you can easily solve this problem using the solution of this problem. Right? So that is the concept of reducibility. Now, how much time it is taking to solve this problem using the solution of this problem? How much time we need to take? We just need this part, right? That means constant. Right? That means constant. Although I'm taking this example, but it is totally irrelevant with your NP class or PNP. I'm just trying to help you to understand the reducibility concept. Reducibility is nothing but to utilize the solution of a different problem to solve a unknown problem. So let's dig deeper into that. we represent reduction or reducibility like this: A less than equals to B means A is reducible to B. Problem A is reducible to B. Okay. Now think B is known to be a hard problem. Just think B is known to be a hard problem. Now you can, okay, just opposite. A is known to be a hard problem. Now, if you reduce A to B, then what kind of problem B is? A is hard problem. A is difficult problem. If A is difficult problem, what can you say about B? Is it difficult or easier than A?
Harder.
Harder. This less than equals to, just think of this way. So A is less than equals to B means is hardness of A is slightly lower than hardness of B. Means B is harder than A. Think this way. B is harder than A. Now, if A is known to be difficult problem, then B is easy or difficult? Difficult, more difficult than A. So we'll utilize this concept. So just think A less than equals to B, very easy to remember. Less than equals to means this one is easier than this one. Here our goal is to find out who is harder. Okay, who is harder? Harder means we can say that this is NP complete. So let's quickly go through this way. And before that, so let's try this. It means A is reducible to B in polynomial time. You can reduce problem A to B in polynomial time. In our previous example, we convert that problem A. Problem A was previously AX plus B equals to 0. And B was C squared plus BX plus E equals to 0. Right? And we use the solution of this one to solve this problem. This one is reducible to this one. And how much time we need to spend for that? Like C equals to 0, D equals to A, E equals to B. That means in, sorry? Yeah, constant time. Because we just need to assign this value. So we can reduce this problem to this problem in constant time, means in polynomial time, right? So our goal is we need to reduce a problem A to problem B in polynomial time. So what is NP complete? One is, it is the hardest problem in NP. That's okay. Another one is hardest NP. Another one is you need to find one problem which is known to be NP complete, and you need to reduce that problem to this unknown problem. Okay, so how we write that? X is NP . So A is known to be NP complete. Our goal is A is known to be NP complete. And our goal is to reduce A to this new unknown problem X. Then we can say X is also NP complete. That means we need to prove that X is harder than known hard problem. This is already known hard problem. We need to prove that X is harder than that. That means obviously X is hard problem, right? Any confusion, any questions so far? Are you on track? Is there anyone who is struggling? Okay. Now we'll try to understand this concept in a better way. It is given that this reduction relation is there, and it is saying that B is a polynomial time algo or problem. So B has polynomial time solution. Means you can solve B in polynomial time. What you can say about A? Can you solve A in polynomial time?
Yes.
Yes. Obviously. Because from this relation, you know B is harder than A. And B is also can be solvable in polynomial time. Obviously, A can be solvable in polynomial time. Right? Okay. Now, let's say A is polynomial time algo. What you can say about B? What you can say about B? It is harder than A. But can you say anything about whether B belongs to P or NP? It can be anything. So we can't make any comment on that. Because A is easy problem and A can be solvable in polynomial time. But we don't know about B. B is harder than that. We know that. So we can't make any comment on that. Great. Now, it is saying A is not a polynomial time algorithm. What about B? It can't be, right? So B is same. B is not a polynomial time algorithm. Okay. And what about A? It is saying B is not a polynomial time algorithm. What you can say about A?
No.
B is not a polynomial time algorithm. A is easier than B. What you can say about A?
It could be polynomial, it could be.
Either one. We don't know. That means we can't make any comment on that. Clear so far? Okay, great. Now, try to understand one concept. A less than equals to B, and we used one example, ax plus b equals to 0 as problem A, and B was cx squared plus bx plus c equals to 0. Now, when we say problem A is reducible to problem B, that means all instances of this problem can be solvable using this problem, right? That means you need to make sure that all instances of this problem can be handled by this problem, but not vice versa. Right? Yes. Yeah, great. Because it is a general case of this problem. Problem A is a general case of problem B. Okay? Great. Now, let's take this one. NP complete. What is the informal definition we got from as for NP complete? First of all, it is hardest NP. and X is NP complete. If so, X is unknown right now. X can be NP complete if all problems in NP is reducible to X. It doesn't matter, all or one. We'll come to that point. One equals to all. If you got solution for one, that means you have already got solution for all. So it doesn't matter. So there is A and B. Okay. Now suppose A is known to be NP complete and B is unknown. Okay. B is unknown and A is known to be NP complete. Now, which relation you need to prove? This one or this one? You need to prove that B is also NP complete. Okay, B is currently unknown, A is known to be NP complete. Now your goal is to prove B is NP complete. Now, which relation is correct way to move forward? Which one? One or two? What it is saying? Which one is harder? A is harder. But our goal is to prove the hardness instead of easiness. Here our goal is not to prove the easiness of this unknown problem. Our goal is to prove the hardness of the unknown problem. We need to prove that this is harder than this known hard problem. This one is saying the easiness, but this one is saying the hardness of problem, unknown problem B. So our goal is to prove that this unknown problem is harder than known hard problem. Clear? So right now we will prove. I'll give you one known NP complete, then we will prove the unknown problem is also NP complete. So we need to make sure which way we need to move forward. This is the correct way. This is the wrong way. Clear? We'll take a couple of examples, then it would be very, much more easier to grasp the concept. So far, any questions? Is it difficult to follow me? If we take the example, this part will be clear, I can assure you. So again, just keep this in your mind when I write this way. That means Y is harder than X. It's not, theoretically, it might not be a correct statement, okay? But to memorize the things, it's best way to remember like this way. It will not make you confused. As well as our goal is always to prove the hardness of an unknown problem. It is our goal. So that we prove that that unknown problem is also NP complete. Do I proceed? Okay. Now, so after giving two informal definition of NP complete, now we'll provide the formal definition of NP complete, the actual definition. And you will understand how we build the solution, the definition. Do I erase this part? So this is the formal definition of NP complete. First, you need to prove that suppose L is some unknown problem. L is unknown problem, and when we can say L is NP complete, first condition is L belongs to NP. L belongs to NP. See, this is NP. NP complete is the hardest part of NP. Okay, so it comes under NP. So it should be under NP. L belongs to NP. And what NP defines?
Polynomial.
No. What is NP, class?
NP, it can verify things in polynomial.
Right. That means L is verifiable in polynomial time. That means L is verifiable in polynomial time. So when we say L is unknown problem and you need to prove that L is NP complete, first you need to prove that L is verifiable in polynomial time. Last day we saw a couple of decision problems which can be verifiable in polynomial time. Like TSP, decision problem, not optimization problem. Subset sum. Those can be verifiable in polynomial time. So first condition is L belongs to NP. That is, L is verifiable in polynomial time. Try to understand this concept clearly, because you will get one quiz. It carries 20 points something, based on only complexity classes and one question from approximation algorithm. And you will get questions like that. I'll give you one problem which can be verifiable in polynomial time and something. Then what you can say about this problem L? Is it comes under P? Is it condition is L star or some problem belongs to NP complete, means these are some known NP complete problem, and you need to prove that L star can be reducible to L in polynomial time. So you need to prove that L star can be reduced to L in polynomial time. Clear so far? So these are the two conditions to prove an unknown problem is NP complete. So the first condition is that unknown problem is verifiable in polynomial time. Second condition is L star is some known NP complete problem, known difficult problem. And you need to prove that that known difficult problem can be reducible to this unknown problem in polynomial time. Clear? So these are the two conditions that you need to satisfy to say that an unknown problem is NP complete. And this is the formal definition. That's why I was taking so much time to discuss those informal definitions. Otherwise, if I directly give you this definition, it would be difficult to understand, right? So clear so far? Now, what would happen if there is some problem which doesn't belong to this NP class? Means particularly optimization problem, TSP optimization, means which cannot be verifiable in polynomial time, but it satisfied this condition, second one. That means known problem can be reducible to that optimization problem in polynomial time. Did you get the point? Means condition 1 is not satisfied, but condition 2 is satisfied. If that happens, then we call it NP hard problem. NP hard means only condition 2 applies, not condition 1. Means it is not verifiable in polynomial time. So if we draw like this, NP hard will come like this way. Or if you draw like this, NP hard will come like this. So we can modify the formal definition by saying that L is NP hard, right? So we can modify the definition of NP complete by replace this condition 2 and say L is NP hard.
You said NP hard only condition 2 applies.
Yeah, but there would be some overlap where there would be some problem which are NP hard as well as NP complete. Some problem. But if it is not NP complete, but it is only NP hard, I should rephrase this. If it is only NP hard, but not NP complete, that means it is satisfying only condition 2, not condition 1. So clear? So let's revisit what is P. P is solvable in polynomial time, verifiable in polynomial time. What is NP? It is only verifiable in polynomial time. What is NP complete? It is, first of all, it belongs to NP, means it is verifiable in polynomial time. NP complete means it is verifiable in polynomial time. At the same time, it is NP hard. Now, what is NP hard? NP hard means any problem which are known to be NP complete can be reduced to this NP hard problem in polynomial time. Clear? So you need to understand P, NP, NP complete, NP hard, these 4. This is the most important concept. And this relation P is the easiest part. This is NP, means it can be verifiable in polynomial time. We don't know whether P equals to NP, means we don't know whether it can also be solvable in polynomial time or not. We don't know. Then NP complete is the hardest part of NP. Hardest part of NP. What is NP complete? It is a part of NP as well as it is a part of NP hard too. Okay. And what is NP hard? NP hard, you may think it's the hardest problem, the exponential one, optimization one, which cannot be verifiable in polynomial time, but there is known NP complete problem which can be reduced to this hard NP hard problem in polynomial time. Clear? Now here in this Venn diagram, it is saying P is a subset of NP. And this Venn diagram is saying P equals to NP. Which one is correct?
As of now, the first.
So we don't know the answer. We don't know the answer. It is an open problem. We don't know whether P is a only subset or proper subset. We don't know. It's an open problem. And one thing is, this is NP class. And in NP class, you will have TSP, decision, and many subset sum, all problems which we do not have any efficient solution so far, but can be verifiable in polynomial time. But it is said that if you can find out a solution for a particular single problem which belongs to NP, it will lead to a single solution will lead to all solution under NP by reduction. So we can reduce one problem to another problem. We'll see right now. So just remember this relation, we don't know what is the relation. It is an open problem. But what community feels that this is the right relation. But no one can prove that so far. So let's take one example. Are you aware of Hamiltonian cycle?
What?
Discrete math, graph theory. Hamiltonian cycle. So what it is saying, given a graph, determine if the graph has a simple cycle that goes through all vertices. This is Hamiltonian cycle. So given a graph, you need to determine if the graph has a simple cycle. Last day we talked about simple cycle. Simple cycle means there should not be any repetition. You will visit one intermediate vertex only once, except your starting vertex. So cycle means you have to come back again to your source vertex. So it should be a simple cycle that goes through all vertices. So you need to determine whether a graph has Hamiltonian cycle or not. So let's take one example. Okay. So first tell me, is this graph in this graph, can you find any Hamiltonian cycle? First of all, what is Hamiltonian cycle? You need to find a simple cycle that covers all vertices. So A, B, C, D, yes. What about this one? Can you find any Hamiltonian cycle which cover all vertices? And it should be simple cycle. It is important. No repetition. So it's not possible, right? So you have understood what is Hamiltonian cycle. Okay. Now, first of all, it's very easy manually to find out whether there is an Hamiltonian cycle or not for this small example. But what is the brute force time complexity? If you apply brute force, means you will apply all possibilities. Then what would be the brute force time complexity? It would be n factorial because you need to explore all possibilities. So it would be exponential. So it is NP complete. So what our goal is, so we'll use the concept of reduction, okay, and the definition, the formal definition of NP complete. So what it is saying, given that Ham cycle or Hamiltonian cycle is known to be NP complete. So it is given known problem which is NP complete. Now you need to prove that TSP decision is also NP complete. So we'll apply the formal definition of NP complete here to prove that an unknown problem is also NP complete. And we'll do step by step. Are you with me? Do I proceed? Okay. So first tell me what is the definition, formal definition of NP complete? I just gave you the solution, the definition.
It is verifiable in polynomial.
Okay. So the problem L should be verifiable in polynomial time. What is L here? What is unknown here? TSP decision. TSP decision is verifiable in polynomial time, yes or no? TSP decision is verifiable in polynomial time, yes or no? Yes, we did that last day.
Not optimization.
Not optimization, yes, not optimization. Yeah, it is saying TSP decision. We did last day, check your note. So we proved that, not proved, we just discussed that TSP decision is verifiable in polynomial time. So condition 1, TSP decision is verifiable in polynomial time. So condition 1 satisfied. Now what is the condition 2? What is condition 2?
It can't be reduced to a known NP complete problem in polynomial.
Just opposite, just opposite. Just opposite. A known problem can be reducible to this problem, because we need to prove that this problem is harder than known hard problems. Clear? So we need to prove this one, right? It is known problem. It is given that Ham cycle is known to be NP complete. So it is given. It is known NP complete. we need to prove that this problem can be reducible to unknown problem TSP decision in polynomial time. We need to prove that. If we can prove that, then we can prove it will help us to prove that TSP decision is harder than Ham cycle. Obviously, then we can say TSP decision is NP complete. Clear so far? So we need to prove that. So far, try to make sure that you have understood both conditions. Do I proceed? Now tell me what is TSP decision? What do you think? Is there any similarity? What it is saying? Just go through the TSP decision definition, the problem definition. What it is asking for. Simple cycle. And what else? Go through all vertices, okay. Then what else? Cost less than equals to some value t, right? It is clear to you. So T is very similar, right? Both are trying to find a simple cycle which covers all vertices. At the same time, TSP has another point that the cost should be less than equals to some value t. It is clear to you. Now let's assume you have a solution for TSP decision. Let's assume. So this is your solution. Okay. Just assume you have the solution. Now, what are the inputs of this solution for TSP decision? What inputs is take? Graph, the G, and some value, cost value T, right?
Yeah.
And whatever the output it will give?
Yes or no?
Yes or no, because it's a decision problem. Now our goal is to prove that we can use this solution to solve Ham cycle. Our goal is to prove that we can use this solution to solve Ham cycle. Same equation, just think of the equation what we did. We have x plus b equals to 0. We have cx squared plus dx plus e equals to 0. We use the solution of this one to solve this problem, right?
Mm-hmm.
Then we can say that this one is reducible to this one. Are you getting the point? So we are doing the same thing. We are using the solution for TSP decision to solve this problem. Same thing. We use the solution of this one to solve this one. We are doing the same thing here. Okay. Now in TSP problem definition, just go through the first line. What kind of G it needs as the input? What kind of G? Graph. Complete graph. It should be complete graph in case of TSP decision. So G should be complete. But in case of Ham cycle, is there any such constraint? No. So this is one graph. How can you make it complete? Just assume this is your graph. How can you make it complete?
Add lines.
Add edges, add missing edges, right? You can add missing edges. So let's assume this is your graph. To work with this solution, you need to make this graph complete. So you can add missing edges. So now it is complete, right? Now, how you can distinguish between the existing edges and these newly added edges? You need to distinguish between them, right?
Yeah.
How you can do that? Easily. First of all, in case of TSP decision, cost is associated with every edge, right?
Yeah.
But in case of ham cycle, there is no cost associated with that. Right?
Yeah.
So first is you need to make this graph complete. At the same time, there should be some cost associated with that, so that we can use this TSP decision solution, right? But in ham cycle, there is no cost associated with that. Now just think, this is existing edges and this is newly added edges. How you can distinguish between them using cost? Just think.
Negative.
Well, you could say, if it's a one,
Infinity.
there's something there, and then zero, there's nothing there.
Great. Just assume which are existing, put value weight 0. And which are newly added, put 1.
Okay.
What we did, why we did? Because if it is already, if we can find out TSP cycle, simple cycle, for this graph, just think, for this graph, what would be the cost?
0.
0. That's why the existing edge we make edge weight to 0 for existing edges. And for this graph, let's assume this is 0, 0, 0, 0, 0, 0. Now, if you add edges 1, 1 for all other, yeah, it is already, no, it is complicated. Let's make it easier. So this is your graph. Okay. So you need to find out. So this is your graph you need to pass. So first you need to make it complete. So how can you make it complete? And you need to distinguish between the existing edges and completed, this newly added. So all are 0, these are 0, and this newly added 1, 1. And what would be the cost to get a cycle for this graph? What would be the cost? 0, 0, 0, 1. So cost would be 1. And in this example, what would be the cost? Minimum cost 0. When did you get 0? When did you get 0? When there is already Hamiltonian cycle is there, right? The Hamiltonian cycle is there. At that point, you will get cost 0. For this example, there is no Hamiltonian cycle, right? So the cost would be more than 0, greater than 0. Got the point? So here we'll pass G and make the graph complete and make T equals to 0. T equals to 0. If the answer is yes, that means Hamiltonian cycle exists. If the answer is no, that means there is no cost of T 0 or cost less than equals to 0. That means no Hamiltonian cycle exists. Got the point? That means we are able to utilize the solution of TSP decision to solve ham cycle. What steps we need to do? First, we need to make the graph complete and then assign cost T equals to 0. If it is the answer is yes, that means Hamiltonian cycle exists. If the answer is no, that means there is no Hamiltonian cycle exists. Hence, we can prove that ham cycle is reducible to TSP decision. We have not yet talked about polynomial time. Right now, so far, we have proved that ham cycle is reducible to TSP decision. Are you getting the idea?
Yeah.
So it is clear how we can prove this, how we can utilize the solution of TSP decision to solve Hamiltonian cycle. Only two steps we need to do. First, we need to make the graph complete, and then the cost t equals to assign t equals to 0. And if it is yes, then Hamiltonian cycle exists. Draw this figure if it is yes. And if it is no, that means there is no Hamiltonian cycle. Now the question is whether this reduction will be performed in polynomial time. We have proved that we can reduce Ham cycle to TSP decision. That means we have proved that TSP decision is harder problem. Or in other words, this problem is a general case of TSP decision. So Ham cycle is a general case of TSP decision. Or TSP decision is harder problem. Now we need to prove that you can reduce this in polynomial time. So what steps we need to perform? First, we need to make the graph complete. So what would be the time complexity to make any graph complete? Adding edges, right? What things you need to do? You need to add missing edges to make the graph complete. And in your complete graph, what is the maximum edges you have in your complete graph? I told you multiple times. In a complete graph, what is the maximum number of maximum or same? What is the number of edges you have in your complete graph? Complete graph means there should be an edge in between every pair of vertices. So it should be n square. Order of n square, actually. It would be order of n square. So keep that in your mind. Complete graph, we already in your midterm there was a question. Complete graph means dense graph. So in that BFS table, I have shown you one table, BFS, Dijkstra, Bellman-Ford, for sparse graph, for dense graph. So complete graph means maximum number of edges are there. So E equals to order of n square for complete graph. So your initial graph can be like this. Something like this. And you need to make it complete. So maximum number of edges you might need to insert in the worst case is order of n square. So to make this graph complete, it will be order of n square. And what would be the time to make it to assign t equals to 0? Constant. Just assign t equals to 0. It is order of n square, it is constant. So how much total time it is taking? N square means polynomial. So hence we can prove that this reduction can be done in polynomial time. Clear? Therefore, we can prove that TSP decision is also NP complete problem. You will get question on your quiz from here. Okay. So are you getting the concept of reducibility? Reducibility in polynomial time. And if we have known NP complete problem, how we can prove an unknown problem can be NP complete. And we'll use the same strategy. We'll do another one. Yeah, we have time. We'll do another one. We'll follow the same strategy. It would be actually easier problem. So you got the point, right? Okay. Okay, the second problem. Okay, the problem is called set partition. Means you have a set S, you need to partition the set into two distinct subsets so that they sum to two subsets with equal sum. So this is your set. You need to divide into two distinct subsets and with equal sum. Their sum would be equal. Sum of those distinct subsets would be equal. So for this example, can you find any subsets? Two subsets with equal sum. 2, 3, 4. Okay, 2, 3, 4. Sum is 9 and 8, 1. Sum is 9. And for this one, can you get any two subsets with equal sum? No, it's not possible. So in this case, yes. In this case, no. So this is set partition. Okay. Now tell me, which problem that we have already discussed is very similar to this problem? Great, subset sum. Subset sum is very similar to this problem. So now our next goal would be assume that so assume that this set partition is known to be NP complete, and you need to prove that subset sum is also NP complete. And we'll follow the same steps. It would be much easier actually. Okay. Do you start the proof? Okay. So what is the condition 1? What is the condition of 1 to prove that a unknown problem is NP complete?
Be verified.
Can be verifiable in polynomial time. Which problem? Which is known, which is unknown here? Subset sum is unknown. set partition is known, right? So you need to prove that subset sum is can be verifiable in polynomial time. And last day we did that using 2 for loop. So condition 1 is satisfied. That is subset sum is verifiable in polynomial time. That is subset sum belongs to NP. Now condition 2. In your last day note, you can find out using 2 for loops, you can easily verify whether the proposed answer is correct or not in polynomial time. And what is the condition 2? What do we need to prove? So you need to prove which is known. The set partition, and it would be towards left or right? Left. Set partition. And here you will have subset sum. So here we need to prove that we can set partition can be reduced to subset sum in polynomial time. In other words, we need to prove that subset sum is harder than this known NP complete problem. Okay? Up to this, it is clear to you. Same steps. Again, we will follow the same step. Let's assume we have solution for this unknown problem. Let's assume we have solution for this unknown problem. What are the inputs of this subset sum? Go through the problem definition of subset sum. A set
And the number you're trying to find.
and a target sum value, right? Some target value, some value. Clear so far? And what would be the output? Yes or no. Now, how you can utilize this solution for subset sum to solve set partition problem? Set would be same set is, what would be the sum value? Okay, let me give you some hints. This is your whole set, right? For this example, you partition it into 2 subsets with equal sum. Great. So what is 9? 9 is, if you add all of them, divide by 2, then obviously you will get 9. So here T equals to sum by 2. So the same set, and you will divide T equals to sum by 2. And you will check whether you get any subset of this sum. If you get that, that means for this example, sum is 9. So your goal is to find out whether there is any subset of sum 9 or not. Clear? Yeah. And obviously it is in polynomial time. So we have studied reduction as well as NP hard. This part is actually NP hard. It comes under NP hard. So you have understood the concept of reduction and the formal definition of NP complete. When we say that an unknown problem is NP complete, first you need to prove that that problem can be verifiable in polynomial time. Second condition is you need to prove a known problem can be reducible to your unknown problem in polynomial time. These are 2 conditions. Okay, so let's summarize what we have studied so far. So the major important part is complexity class. B, what P stands for? Easy problems, means problems with efficient solution. Efficient means polynomial time, like BFS, DFS, Dijkstra, all comes under class P. So this is class P. And P, please remember, P is solvable in polynomial time. Therefore, P is verifiable in polynomial time. So P also comes under NP. So what is NP? What is NP?
It's verified.
It is verifiable in polynomial time, but we can't say any comment on whether we can get any solution in polynomial time or not in future. And what is NP complete? It is the hardest part of NP. It is the most hard NP problem, you may think. Okay? And the level of difficulty, you may think like this. P is the easiest part, then NP complete, and you may think NP hard like this. Okay? And these are the level of difficulty. And again, we don't know the relation of P and P. We don't know whether they are equal or not. We don't know nothing. We know nothing actually. So these steps should be clear to you. Not difficult, but you have to understand the flow clearly. What is verifiability? What is reducibility? These things needs to be clear. So we are done with complexity classes. Next day, I'm not sure which topic I'll start. Let's see. Plus, please do revise this part, and there is a quiz. The deadline would be most probably by Sunday, and it carries 20 points. I'll release. I have not released yet. I'll release the quiz, and also the scribe notes assignment is due tonight. So submit your assignments with. I expect you will have. You have taken enough notes. So please submit that. I'll go through that. And also I have most probably increased the maximum points for scribe notes. Most likely because it would be really long notes. Okay.
So
A diagram.
Well, that's what I did before, but yeah.